Okay, let's just go ahead and get started. It's great to see so many people here today. As I said, I'm Charlie Nunn. I'm at Duke University in evolutionary anthropology and Duke Global Health. And this is Club Ev Med. We actually like to call it Club Ev Med Conversations because we invite people in to give a short talk on some cutting edge research in evolutionary medicine. And then we open it up for a conversation with the audience. And so we really do want to hear from all of you. We want you to post questions and comments in the chat. And also be prepared to ask questions or raise points afterwards so that we have a productive conversation afterwards. Club Ev Med is organized by a number of different evolutionary medicine centers, and I'll paste that into the chat. These centers all have representation on our committee and help us choose the speakers. And then we also work closely with the International Society for Evolution Medicine and Public Health. And again, I'll paste this into the chat. You have a link there to the society and also some information on our conference, which is coming up. And we want to encourage everyone to please attend the conference July 8th to 10th in Nashville. Afterwards, there's a Scopes Monkey Trial Centennial Symposium. So please consider coming to that too. That's organized by some of our co-organizers in Nashville. And we want to encourage people to submit articles to the Society's Journal, Evolution Medicine and Public Health, which you'll see there. Oh, actually, I didn't hit enter. Okay, there you'll see it all now. Thank you. Okay, so anyhow, this is Club Ev Med Conversations, and we're going to hear today from Chris Venditti and from George Butler. And so I'll just give a brief introduction. Chris is a professor in ecology and evolution at University of Reading in the UK. And for those who don't know this, the evolution group at Reading, it's really at the forefront of developing and applying phylogenetic comparative methods for understanding trait evolution. And I always pay attention to the work that comes out of the ecology and evolution group at Reading, including Chris's group, because it's really the finest and most sophisticated implementation of these phylogenetic methods, and it's done in a very sophisticated and rigorous way. But they also address really big questions. They're very good at identifying important questions. And they always interpret their findings in really innovative but careful ways in light of those questions. So it's a real pleasure for me to feature this paper by Chris and his team on Club Ev Med today. And with us, we also have a member of his team, a former member of his team, George Butler. George received his PhD in Chris's group in 2021. He then went on to Johns Hopkins, where he was a postdoc, and he's now a career development fellow at UCL in their Cancer Institute. He's interested in cancer evolution, specifically prostate cancer, and phylogenetic comparative methods. So as I understand it, George is going to present the talk today, and then Chris and George will be available to answer questions and engage in the conversation afterwards. We would like to see questions and comments in the chat, and if there's something that's pressing that needs to be addressed, we may interrupt the conversation to just ask clarifying questions and things like that. Okay, go ahead, George. Thank you.
Brilliant. Okay, let me just share my screen. Cool, thanks. So thank you for the invitation to speak today. We're really excited about this. We put out a slightly different title in the bio, but a kind of broader way of thinking about some of the work we've been doing is this idea of kind of adaptive mechanisms of cancer defense across species. And just before I go into the sort of work, it's really important to highlight this has been a kind of very big sort of interdisciplinary effort. So I'm now at UCL, but I was previously at Hopkins with Ken Pienta and Sarah Ammond. And this is work that we did with Chris and Joe Baker, who's a postdoc at Reading. And it's these kind of teams that I think really allow us to sort of start to probe these bigger questions. So kind of a brief overview of what the talk's going to be about today. So we're going to go over sort of what is Peto's paradox, some of the challenges of modeling trait evolution, and then this idea of heterogeneity in rates of evolution through time. Then we're going to finish off talking about some of the kind of winners and losers of the anti-cancer arms race. So first of all, what is Peto's paradox? So, let's think broad here. So when we think about multicellular organisms, we know that for multicellular organisms to survive and grow, cells must grow and divide themselves. And with every division, there's a risk of a mutation appearing. So, kind of very basic view of cancer, we can think, well, longer life, longer lived in species or bigger species should have a greater risk of cancer. And this was an observation made by Sir Richard Peto in 1977. And we can sort of, a way to think about this is the idea that if we've got cancer prevalence here on the y-axis and body size here on the x, we'd expect to see a positive association between those two axes. In other words, a bigger species like an elephant, we'd expect to see higher prevalence of cancer compared to a smaller species like a mouse. But for a long time, that's not been observed. It's instead been seen that these two things appear to be independent from one another. And there's been a kind of variety of different studies that have started to probe these questions, but it's kind of access to data that's been one of the challenges up until now. So we're very fortunate that earlier this year there was a paper released by groups down at ASU, um, led here by Zach Compton, which is they've managed to go across nearly 300 species looking at individual necropsy records and record the prevalence of cancer. So this is a massive effort, and we're sort of very grateful to this group for sort of this hard work in collecting this data. And this data set spans across amphibians, birds, mammals, and reptiles. And a kind of another real big strength of this data set is that they've actually managed to go into the data and split out what we refer to as neoplastic growth and malignant growth. So for anyone who doesn't spend a lot of time in the cancer world, neoplastic growth is a kind of broad term for both covering both benign and sort of malignant tumors or cancer, whereas malignant growths are your cancerous tumors. And so kind of conventional wisdom in a lot of previous studies has been to take the number of animals with neoplasia or malignancy for a given species, and then to divide that by the number of animals that you sampled, so the number of necropsies, and then see if that's associated with body size. But part of the challenge here is that proportions, these that we have here on the y-axis, don't necessarily evolve as we might expect in accordance with Brownian motion. And Brownian motion is used as a underlying model for sort of evolution and phylogenetic comparative methods. So over the next couple of slides, I'm just going to run through, and apologies to anyone who's very familiar with this, but how we model trait evolution, just some of the real sort of basics. So if we think about a trait of modeling trait evolution in times, this is over a fixed period of time, we can start off with some size. So at time t, there's some size. And in the future, the size of, say, this species might increase or it might decrease. So we've got bigger and smaller. And those increases and decreases can be small or they could be much larger. So a way to kind of quantify that change is to sort of draw that change from a normal distribution. So we can see here that we're centered around 0, and that if we draw a value that's further up, that would mean that there's going to be an increase in size. If we draw a value further down, there'd be a decrease. And the size of that distribution is controlled by a variance parameter. So bigger variance, bigger distribution, smaller variance, smaller distribution. So that's for a single point in time, but we can apply the same idea to thinking about how traits evolve through time. So the idea here being that you've got these separate chunks in time. There could be an increase followed by a decrease followed by an increase, or it could be continual decreases in size. And again, these changes are being drawn from a normal distribution. So that's a kind of abstract example, but that's the same idea that we use when we think about modeling traits on a phylogenetic tree. So we start off with some size, and the branches, the horizontal branches here, are expected change per unit time. So that's the change, the decrease or increase in size. And we refer to that sigma parameter, that size of those changes, as our rate of evolution. So when sigma is bigger and we have a bigger distribution, or so wider distribution, we can have bigger changes, there's a higher rate of evolution. And in an example like this, that's quite intuitive. If we've got, as I said, that bigger sigma, there's potential for bigger changes. But that becomes a little bit more challenging, that interpretability, when we start to think back to our proportions example. So again, we've got neoplasia or malignancy divided by your number of necropsies, and that's our dependent variable, and then body size, the independent. So let's imagine, for example, that we start off with some proportion of species or individuals that have cancer. So that's about half our population. And then we've got our split of our tree, and we find that for this species here, that cancer prevalence has increased, and for this species, it's decreased. Now, if we think about that variance parameter, we can start to think about that as we were with body size because we have the same denominator, we have the same number of necropsies. But that becomes much harder when we think of this sort of scenario here on the right, where actually for this sort of species up here, we've sampled many more individuals, even though the number of individuals with cancer has actually stayed the same. So it looks like the cancer prevalence is decreasing, but that's as a function of the fact that we're sampling more. And you might say, well, if you sample more and you've still got the same number of individuals, that is a decrease. But the issue is that it becomes now very hard to interpret what that rate of evolution is along a branch. Because in this example here, we're effectively modeling an increase in sample size, not a change in the number of individuals with cancer. So how can we get about doing that? Well, thanks to the sort of advent of various kind of modern modeling approaches, we can actually model now data that's not just normally distributed. So what that means is we can model the amount of neoplasia or malignancy directly as count data, meaning that we can model it as a Poisson process. So now you have your neoplasia and malignancy on the dependent. Necropsies is still included here as an independent variable, so we still account for the fact that some species are going to be sampled more than others. And what we can then look at, after accounting for that difference in sampling, is the association between body size and the neoplasia malignancy. So that's what we did, looking across that data set of nearly 300 species. And we found there was no evidence to suggest that Peto's paradox was there. So what I'm showing you here is a neoplasia on the Y in panels A and B. And you've got snout vent length. That's for amphibians and reptiles. So I should point out we model amphibians and reptiles separately from birds and mammals because snout vent length is used to record size for amphibians and reptiles, whereas body mass is used to record size for mammals and birds. We find that neoplasia is positively associated with snout vent length or with body size, meaning that there's sort of more growth for bigger species. But what's really interesting is when we then look specifically at malignancy, we also find the same association. In other words, bigger amphibians and reptiles are getting more malignancy, and bigger birds and mammals are also having more malignancy. And I should note here that, and I'm not going to go into all the details of the modeling, but the marginal R squared, the sort of goodness fit, it's about 0.6 for amphibians and reptiles, about 0.4 for birds and mammals. So that's high. That's really high. These models are explaining a lot of the variation in malignancy and neoplasia. So we found this and we thought, okay, that's cool. That's an interesting result, but let's step back and think about this. So this is saying that the larger species are at higher risk of getting cancer. Well, we know through things like Cope's law that actually there's a sort of gradual tendency over time for species to get bigger and bigger. And that seems to sort of, juxtapose these results because if you're getting bigger and bigger and bigger, you'd expect more of those species to be dying because they're getting more cancer. And again, these are sort of broad ideas. So one thing we did was we stepped back and said, well, actually, let's think about body size evolution itself. And let's think about the processes that are driving body size evolution. And we know that body size evolution is not a homogeneous process. In other words, that rate of evolution that I spoke about previously is not the same at all points in time for all species. So over the next few slides, I'm going to sort of explain what I mean by that and this idea of kind of heterogeneity in rates of evolution. So in this example here, we've got an elephant that's about 3,000 kilos. And then we've got a small hyrax here that's about 4 kilos. And we know that they have a common ancestor that's approximately 8 kilos in size. So over the same amount of time, one of these species has decreased very slightly, whereas one of these species has increased massively in size. So how do we model that? Because that's such a big difference over the same period of time. Well, what we can do is we can allow the rate of evolution in our modeling to vary for different branches in the phylogenetic tree. So in this example here, the blue branch is being drawn from this normal distribution here with smaller variance, whereas in the red branch, where we've seen this rapid increase in size, we're drawing from this red distribution, meaning that the rate of evolution, so the increase in size per unit time for elephants, is much larger compared to the hyrax. And another way to think about that is that actually there's been more total evolution for the elephant. So if we scale the branches of the phylogenetic tree to reflect the amount of evolution that's occurred, we can see there's been a much greater increase in the elephant. And this isn't just a specific example here with these two species. We can find that there's evidence of rate heterogeneity throughout vertebrates. In other words, vertebrates have undergone repeated episodes of accelerated body size evolution. So we can see here, this is the elephant here on a rate scale tree. We can see how much longer those branches are, leading to modern day elephant. And it's important to highlight here that faster rates of evolution are indicative or can be indicative of positive selection. In other words, there's been strong selective pressure for these species to get bigger fast. And I should say here that on average, fast rates of body size evolution are associated with increases in size rather than decreases. And we can actually measure the amount of evolution that's occurred, body size evolution, by measuring the total path length from the root out to the tip. So in this example here, this species that's on the red branch has undergone more compared to the blue. So again, so we know that bigger species appear to be getting more cancer. I've sort of shown here that there's heterogeneity in rates of body size evolution, and that this heterogeneity is a result of strong selective pressures. So if that's true, and the bigger animals are getting more cancer, and also though they've got faster rates of body size evolution, then we might expect that these fast rates of body size evolution will also reflect the evolution of improved cancer defenses. So that's what we wanted to test. So we did that by taking our model again with neoplasial malignancy, putting the number of necropsies, body size, and then the pathwise rate. So that is that path length from the root to the tip. And we put this in our model. So what I'm showing you here on panels B and D is your neoplasia prediction or malignancy prediction against body size. So in the model, even with pathwise rate included, we still find that there's positive association between malignancy and body size, or neoplasia and body size. However, interestingly, we find that there's a negative association there between neoplasia and malignancy and pathwise rate. So just to kind of spell that out a little bit, because there's a lot of moving parts here, this is saying that bigger species are getting more neoplasia or malignancy, but also species that have undergone more body size evolution, of which are typically bigger themselves, there's a decrease in their malignancy or neoplasia. And that might sound a bit heady, so another way to think about this is a sort of graphical example. So the dotted black line here is the amount of malignancy that you'd predict for different body sizes if you had a sort of homogeneous rate of evolution. So if you didn't account for the fact there's this heterogeneity in body size evolution, the dotted black line is what you'd expect to see. Whereas the thick black line here is the amount of malignancy that you'd expect to see after accounting for that variation in total body size evolution. So the difference between these two lines is the amount of malignancy that you're sort of losing or gaining, whichever way you want to look at it, after accounting for this rate heterogeneity, meaning that bigger species like an elephant are benefiting much more from more total, more heterogeneity and sort of faster rates of evolution compared to smaller species such as a bat, which is an interesting thing to think about because it means that these larger species that have got big and the selection's acted very aggressively on them to get big quickly have somehow managed to pick up some sort of cancer defenses. So it's saying, to hark back to our original Peto's paradox, yes, these bigger species appear to be getting more cancer compared to their smaller counterparts, but also selection's acted on them in some way, some sort of sort of molecular mechanisms in these species, mean they don't incur the same cost as you might expect compared to their smaller counterparts. Um, and so that's a lot of sort of heavy kind of statistics and a lot of sort of ideas thrown at you. But just to highlight, we can also start to take these models further and identify which species are the real winners and the real losers. So what I mean by that is when we fit a model, there's always going to be some kind of variation between what we actually have as our amount of neoplasia or malignancy and what's predicted. So in this case here, each of these green dots would represent a species. The gray line there would be your prediction. And you can see that as a general rule, most of these dots would cluster around the line. But there's these one or two species that appear to be getting much more cancer than you expect, or actually the kind of inverse as well. It's these species where their level of cancer is much higher or much lower than you'd predict. So we did that with this data set and took it further. And it's interesting because a lot of the species that came out as being sort of exceptional for the amount of cancer they get, so they're getting much more for their size, are species that we know about. So stuff like the budgie, for instance, very common for renal cancer. The four-toed hedgehog getting a lot as well. Ferret and things like that. And what's interesting, and just something I want to point out here is when I say exceptional, this doesn't mean species that are getting no cancer or they're all getting cancer. It's just the difference in what you'd expect to see relative to their size. So anyway, that's a bit of a whirlwind of this paper. Feel free to read it if you want to go any further. And with that, yeah, any questions you might have for Chris or I or anyone. So thanks.
Thank you, George. That was great. I like the introduction to the phylogenetic comparative method. You made that really accessible.
Cool.
We have yes, I see some hands clapping. Um, okay, we have plenty of time for questions. I can certainly start if nobody else has questions. I can kick off with a few, but I'd love to hear from some of the people in the audience first. Does anyone have any questions to get us started? Joel Meyer has a question. Joel, good to see you here. Do you want to ask your
Thanks,
question?
Charlie. Sure, yeah. So I'm curious if there's enough data with age distribution in your species to ask the question of whether the selective pressure that you're presumably seeing here is affected by the age at which the neoplasms or malignancies occur. In other words, assuming that later life neoplasms or cancer just have a smaller effect in terms of reproductive fitness than early life ones would.
No, yes, a brilliant question. So we did test the longevity of the species and the age at death because this is from zoological specimens. And at least in our models, we found that there was sort of no association between that and the amount of cancer that you'd expect to see. Now, there's a couple of caveats there. One being we were doing that on a reduced sample size. We didn't have quite as many species because it's just not as available necessarily longevity. And two, you've got this interesting sort of interaction between what's going on at the species level versus the individual level. So everything here is just aggregated at the species level, but I think there's interesting questions there to tease apart with what would be going on at the individual level. So to your point, is there a difference between those sort of, for a given species that are much older when they're getting cancer compared to the ones that are much younger? And I think that'd be a great question to ask.
And maybe just to clarify, when you said longevity, do you mean the longevity of the species? I'm almost thinking about sort of the reproductive age. In other words, were they getting
Oh,
cancer when they were still reproductive, or were they getting cancer when they were post-reproductive?
no, yeah, sorry. Yeah, so I meant the longevity of the species, but yeah, to your point, that's a fantastic question to pose, right? Because like you say, sort of who cares if you're getting cancer if you've sort of passed on your genes?
Right, right. Thanks.
Thanks.
Great talk.
Thanks.
Good. Thanks, Joel. And I guess it might be worth pointing out that, there are only like 4 or 5 mammals where there's any convincing evidence of post-reproductive lifespan at all, anyhow. So a couple of whales, humans, a population of chimpanzees. But really interesting question. I was also interested in the longevity side of that and whether that was a predictor. Let's turn over to Carlo. Carlo, you have a question.
Yeah, thanks. I think we also put this in a letter to PNAS. Um, George, I really like the rate heterogeneity work. I think it's a fascinating result about how the change in body size, in fact, it goes against what I would have predicted, a sort of evolutionary lag. I would have expected faster evolving species to take longer before they build up the cancer defenses to match their body size. So I think that's really cool and should be followed up on. If we could go back to your statistical method, um, I have some issues with the model you guys are using. If I understand it correctly, within a group like mammals, the variable that's the number of necropsies estimates a single rate, like prediction of the proportion of those necropsies that's going to be cancerous. So the model assumes that all mammals have the same cancer rate, except there's another variable, the body size, that allows different mammals with different body sizes to have a different additional fixed number of malignancies. Am I understanding that correctly?
Yes, the model's set up such that you've got some variation in the amount of malignancy that's as a result of the fact that you've got more or less sampling. So we have that in there to explain that variation. And then you've also got some variation in body size, and that's what we're interested in testing.
Right. So, for example, maybe that the coefficient on the number of necropsies is like 1%. Like you expect 1% of mammal necropsies to show cancer. And then if you're an elephant, you get an additional 10 malignancies. And if you're a mouse, you get only one additional malignancy, something roughly like that, right?
Okay, yep.
Okay. So then if you went out and sampled 1,000 more elephants and 1,000 more mice, you would only expect 10 more necropsies with malignancies in the elephant and 10 more necropsies of malignancies with the mice. Because there's no interaction between body size and number of necropsies.
Yep.
So that seems weird to me, that the body size wouldn't have any relationship to the proportion of necropsies that have cancer.
Do you mind if I speak a bit here as well? So we tested the interaction between body mass and number, and it isn't empirically significant.
Okay.
It's one of the things that we investigated. But I'm not sure
That's actually, so that suggests that there isn't much of a Peto's paradox if there's no relationship between the interaction between body size and number of necropsies with cancer.
No, why does that shouldn't? So if your definition of Peto's paradox is that it's associated with size, that means there is.
Well,
that is still true after accounting for that number, right, of necropsies.
Well, it's kind of a weird model because you have this fixed number of additional cancers from body size, but it doesn't matter how many more necropsies you do. It says.
No, we simultaneously estimate that, right? So given the data that we've got, we estimate that the bigger body mass species have more cancer or malignancy after accounting for the number of necropsies, right? They're simultaneously estimated in the model. So you can say that the data's biased if you like, but given the data that we have,
I mean,
those paradoxes rejected, right? That's still true.
So yeah, I mean, okay. I mean, we have sort of different models in our heads about how the relationship between body size. I mean, I think that the question about Peto's paradox, and of course, our paper also showed a positive relationship between body size and malignancy. The question becomes then
after accounting for gestation length, right?
Yeah, without accounting for it, you can still see a relationship with neoplasia rate, but not malignancy. But once you account for gestation, which goes in the opposite direction, which we think sort of masks that effect, which I think is the right model to as far as we understand the factors. But I think then the interesting question is what is the expected number of, or what is expected relationship between body size and cancer? Like, I think that there's a small increase with body size. But then we have to argue about, well, how many do we expect? Do we expect having 100 times more cells? We don't really expect a linear relationship between the number of cells and amount of cancer. And so, we've looked at Shibata and Calabresi's models of the relationship, and of course, there's the old Armitage and Dahl models. But I think that's sort of the next interesting step here to ask, okay, if there is a small positive relationship, is there still evidence of cancer defenses? In more cancer defenses in larger animals, or is there's evidence that they all have basically the same biology per cell?
Yeah, I think that would be really interesting, actually. But and this is something we've also looked into. There's very little data on number of cells, across species. I mean, there's a data set, I think, of maybe a handful, maybe up to 10 or 20. George, is that what we found?
Yeah.
So to really probe that question, it'd be really fun to get those data.
I agree. Yeah, we're just using mass as a proxy, right? But
yeah, nobody really knows the relationship, because I think if I understand your argument correctly, I think it assumes there's a one-to-one relationship between mass and cell number. And we're not really sure about what that is across species, I think, at the moment. It seems to be variable given the small amount of data. But I guess this is exactly why it's really cool to ask these questions, and hopefully in the future there's going to be more of these kinds of data that we can probe the questions.
And by the way, we're really delighted that you guys have been able to pick up our data and be able to analyze it. I think that's one of the main goals, was to provide a resource to the community. So thanks for doing that.
It's an amazing data set.
Yeah, thank you.
Okay, let's move on to Vaughn. Thank you for that question, Carlo, and for the discussion. Vaughn?
Yeah, thanks. Fun topic as always. This is really for all of you who are working carefully in this area. The question really is about the evidence of lineage level selection or lineage sorting, and the extent to which you can account for extant lineages, successful lineages, potentially containing bigger creatures having displaced lineages with potentially higher cancer rates as they've gotten bigger, or not. I'm just curious.
Do you want me to go, George?
Yeah, go for it, Chris.
Let's see if I understand fully the question.
So really, it's really phylogenetic autocorrelation and the extent to which deep lineages may have displaced other lineages. And of course, you'd need an example of a remnant species from the displaced lineage to compare against.
Yeah. But we obviously don't have that information from the fossil record, right? But it's an interesting thought experiment. So here's what I think we can say. So we can use the body mass of mammals and birds and all the different vertebrates to infer rates of evolution. So the speed of evolution along the branches of a phylogenetic tree. Then we know, or we can do some statistical tests to see whether there's a bias in terms of whether those rates lead to larger size or smaller size. In all of the cases of the trees here, we tested that in the supplementary in our paper, and we found that in all of them there is a bias. So where you see higher rates of evolution, it's towards bigger size. Now, when you put that in terms of historical data that has the fossil record, we can make decent comparisons with mammals because their fossil data is very good. What we can infer about the past size is similar to what we see in the fossil record for mammals. I don't know about the other groups because the fossil record is much more sparse and we can't make those comparisons. And therefore, when we can include that in our overall models, we can say that that bias is perhaps associated with something that the species is doing to mitigate the risk of cancer. And we can't say what that is, but it definitely seems linked. So while it would be great to have a time machine and go back and look at cancer of past species, but I think it's indicating that there is some resistance being built up, and we could speculate then that, you know, newer, if you like, or, you know, derived species were out competing the historical ones based on the fact that they weren't getting some level of cancer, perhaps. But the mechanism is really difficult to tease out from these analyses, right? We've got no idea, I guess. Well, maybe the others do. Do you, George? I don't.
No.
Thanks.
I think that's all what we can say. but I'm not sure it speaks exactly to your question, but I think it at least talks around the issues involved.
Yeah, I mean, I think I was just hoping maybe you have examples of lineages with, you know, a few orphans that are old species, and then say newer lineages, newer, more speciose lineages, and you can ask whether there's any evidence of right sort of phylogenetic inertia related or lineage sorting related to anti-cancer mechanisms that evolved at the root.
So you would perhaps be seeking a analysis which looked at the rate of speciation rather than the rate of morphological evolution. Yeah, that might be interesting to test.
Yeah, thanks.
Yeah, that's an interesting idea. Yeah, a study of diversification rates. And
right.
Yeah, that's interesting. Has anyone ever done that? Carlo or others? Anybody? Or Chris, do you know of any? In terms of the cancer data set?
It wouldn't
Not
be
in the
hard.
cancer field. Yeah.
I mean, we can estimate speciation rates in multiple ways, so the analysis is totally possible.
Yeah. Okay. Thanks for that question, Bob. Barb, would you like to ask your question? Good to see you.
Sure. Hi there. Great. Well, first of all, Chris, thank you for this new and exciting contribution to this emerging field. My comment is sort of a question or maybe a challenge for all of us to sort of reflect on, which is some of the peril of treating cancer as a homogeneous disorder. And I say that, and let me just anticipate and say that I mean, it's incredible that this data is available, that these necropsies are increasingly available to us, and that there are limited numbers. That is what it is. But you know, if you look across the types of cancer, in other words, if we're not calculating these rates with the type of cancer in mind, the kinds of errors that we might be pulling in inadvertently include, we know that there are very tissue-specific differences in the selective pressures. So, for example, colonic epithelium turns over every 4 to 5 days, whereas a number of central nervous system cells have much longer, you know, much less turnover. Those are biological characteristics that are very relevant to thinking about cancer vulnerability. So if we're treating cancer as cancer writ large as a biological characteristic and not factoring in these fundamental differences in the mechanisms that underlie the differences in vulnerability to specific cancers, I think we are potentially, I think the approach is right, but we may be it may be a self-inflicted injury. One of the examples that I was just kind of working on was certain resistance to melanoma among certain reptilian species, but some of the mechanisms through which that resistance emerges, it's probably why hematopoietic cancer, I mean, leukemias are very, very common in reptiles and snakes particularly. So, but also in some anurans. So I'm wondering how to reflect on that and how to think about that. So, because if our goal is to identify species and the species in which resistance to cancer has emerged, sort of taxa-specific vulnerability, and if some of those biological characteristics, right, are going to be either conferring resistance or enhanced vulnerability. I'm just wondering if you've addressed that, and forgive me if that was addressed in the paper and I didn't see it.
No, yeah. So that's a wonderful question. So to your point exactly, with the sort of individual specimen level information, so knowing, you know, of the tens, you know, species X that died, 5 of them had this cancer versus 3 had this versus 2 had that. You can start to really sort of untangle those questions. So I think, and you know, Carla would have a better feel for the data that is and isn't available. But if that data is available, you could really start to unpick some of those questions. And you know, it starts to get really interesting, right? Looking at the interplay between sort of interspecies dynamics, which is what we've sort of focused on here, versus intra-species dynamics, which starts to then probe exactly those questions, you know, and there's a whole suite of different methods and approaches you could do to really tease that kind of detail apart. But I think it's a
Yeah.
wonderful question.
Yeah, I'm just
Another
wondering,
thing-
and yeah, go ahead.
Sorry, I was just statistically speaking, or in terms of I mean, it's a really cool idea to test this or account for different types of cancer. I'm not a cancer biologist. I don't really understand which ones, but so statistically, if we had the data, it would be really interesting to test the differences in the different types or categories of cancer. And we could do that really relatively easy if we have the data. But as far as I understand, we don't have that data yet. The other thing which is interesting to speculate on is at the moment, given what we do know and the data we do have, is there a size bias in the types or categories of cancer that could explain the results that we see? So given that we can't test that, is there, and I don't know the answer, you might tell me, yeah, absolutely. Is there some reason to expect that you get more types of cancer in bigger animals, or you get more prolific cancer in bigger animals per, I don't know. But on the flip side of that, I think there are still speculations that groups like this can still talk about and give interesting insights on, given the results. So yeah, sorry, that was just to add a bit of fuel to this fire. I think that there's a lot of ways to try and think about these things, and if without the data, we can try and see if we can think of any potential biases that might explain the results.
Yeah, and Avani Mittal had a question along these lines as well, and Carlo answered it in the chat. And Carlo, it looked like you were just about to speak. Do you want to add to this? Go ahead, please.
Yeah, I do. So this, thanks for the acknowledgement about the Herculean task here. It was actually a 10-year project that just finished, collecting up all this data and getting permissions from 100 zoos. But there is a really great data set that Matthew and Arcelia that are on this call have accessed through Species 360. It's the ZIMS data set. I'm not sure how many necropsies they have, but they've got 13 million animals in their data set. But their database is set up only for basically husbandry of individual institutions to monitor their animals. So you can't do a query and say, give me all the mammal necropsies. It just collapses. So we've been putting in grants to fund a refactoring of their database to turn it into a scientific tool, and we haven't gotten anywhere. So this is sort of a plea to the community about the importance of investing in the development of these data sets. And there's a gold mine there, and Matthew and Arcelia have done great work, I think, mining it. But it's a heavy lift at the moment to do that.
Yeah, I've had some experience with that exact same problem with some other questions. It's really difficult to query their, well, I mean, it's impossible. And they seem to, they can give you very basic information very quickly, but I think it's not set up yet to actually be able to get some really interesting information, which is rich in those data. So I've had the same experience, not just with cancer data, but with other data as well. So again, I think that would be a really valuable thing to try and achieve.
Barb, did you want to ask another question, or Carrie?
Just a follow-up to Carl, to all three comments, and one, I think, exciting, I mean, possible way of approaching this. So glioblastoma would be kind of a good example, because if assuming the rate is in humans is whatever, we're going to assume it's about 1 in 100,000 individuals, human individuals, who develop glioblastoma. So if we assume that that's the same, the chances of we're never, even if every zoo in the world, I mean, we can't get enough numbers. It's just not possible. But is there a workaround? And one approach could be to maybe identify the top 15 or 20 high impact cancers, and to then really start with the known mechanisms in humans of vulnerability, and these are extensively mapped, and use that as part of our comparative, from the outset, our comparative approach. So when we're looking at the genomes of the candidate species that may be identified from an initial survey, but to really not, I mean, it is Herculean, it's amazing. These data sets are unprecedented in terms of how many, the numbers are huge, but we're never going to have the numbers that we need to use this methodology alone to get the information that we want about not only taxa-specific, it's taxa-specific vulnerability to specific cancer types. But I think there's a pairing of methodologies that could do this successfully.
I think that's a good point for the rare cancers. I think where we do have a little bit of traction is in these species that get a ton of cancer, like the ferrets, and it's mostly lymphoma. So if you look at the high end, they often seem to have a bias to a particular cancer. And we're hopeful that some of these animals could be natural models of spontaneous cancers of particular types.
Okay, George and Chris, I had a question about the I actually had two questions about the exceptional species. The first question is just kind of a statistical question. I imagine that for some of these, for a lot of these exceptional species that, really had large deviations from the model, that it had something to do with small sample sizes, small number of necropsies. I was just wondering, what does the sample size range from, and are they associated with small sample sizes where you just had a, kind of a poor estimate of the rate of cancer in those species? And likewise related to that, have you thought about doing a weighted regression or something like that to try to control for not just control for the sample size, the number of necropsies in the regression model, but the weight of the different degree of sampling in the species?
So all of the species have a minimum of 20 necropsies. To your point, there is obviously variation. In some species are sampled much more and much less than others. I can't remember off the top of my head whether the exceptional species are all the sort of lower end of that spectrum. I don't think they are, but I can certainly find that out and sort of get back to you.
It seems unlikely, like a chicken. I don't know, but it seems unlikely chicken must be sampled really
Yeah.
highly, right? And same with ferret and budgie. They must be really widely reported, I should think.
Okay.
Yeah.
But
That's
it's interesting, Charlie. I think this is something that you were one of the first to do, right? That is where you account for research effort. Is that what you mean, right? So it would be interesting to try and account for research effort in this. But do you think it would be highly correlated with number of necropsies, perhaps, like really highly correlated? Because I think that is in some way evident, but it would be interesting. That's something that we
Yeah,
could
if these are zoo animals, then it's correlated with their appeal for zoological collections,
yeah,
than research effort, I guess.
yeah. So it might be interesting to look at that kind of stuff as well. But we didn't do that in our work.
Okay. The other question I had was about involving these exceptional species, has to do with some of the work I know you're familiar with, Chris, where you essentially try to predict what a species would, what its phenotype would be, based on the other species in a clade, and then you ask, is it exceptional in some way from those predictions? And I was, really thinking about that in the case of humans. I mean, if you thought about where humans fall on all this in terms of whether we're an exceptional species and trying to apply these models, to make a prediction for what the rate of human cancer would be and what that compares to.
Yeah, so to answer the part about humans are difficult, right? Because we've got, there's been sort of rapid domestication of humans, right, over the last however many years. And, we've got the advent of sort of modern medicine and so on and so forth. We did plug into the model, if you took an average human size, we know the amount of body size evolution to humans, and then you just took the average number of necropsies. This is very loose, right? And this was something we did just out of personal interest. And the cancer prevalence was more akin to a species the size of a bat, which is sort of kind of jarring to think about, right? So yeah, I think there's some interesting questions there to start asking with humans.
Say that again. Give me some more details on that, George. What do you mean by this? You mean
No, sure. So we
much
took
lower than expected.
so the so from the modeling point of view, right, we just plugged in the sort of parameters into our estimated model, which would mean that that the humans are getting less cancer, right? Which is really counterintuitive. But I think this is where you start to have to be really careful, right? Because we've got things like the age effect in humans. We've got the fact that perhaps there's certain conditions in humans that would like other species wouldn't have been able to withstand for that long, and kind of we keep humans alive with various conditions and ailments that perhaps wouldn't be the case for species. I don't know if Chris wants to add anything further to that. He's more of a hominin expert than I am. So
So I don't know. We just did that calculation. It was just a journalist that asked, right? So I'm not convinced we're happy about its robustness. So I'm not sure about that. But I think also the thing about humans is we do have a massive rate of evolution as well. So, you know, that's probably not accounted for in what we were doing. So I'm not sure about that particular result. But to your other part of your question, Charlie, we actually implemented a phylogenetic prediction of the type that you're describing in this model. So those outliers were determined by that method, essentially, and a type of methodology like that. It was implemented in the Poisson model rather than in the usual way that we would with a simple Brownian motion one. But it's the same methodology.
Excellent. Thank you. Okay, there's time for one more question. Anybody have a question to close things out, or a comment, or a suggestion? Okay. Thanks, everybody. And Michael has a point. Okay, yes, I remember that paper. That's a nice paper, Michael, in Ecology Letters. Okay, thank you both. Thank you, Chris. Thank you, George. Really interesting paper. Great to have so many people on the call today and sharing perspectives. I think this is a really productive conversation. So
Thanks very much.
Brilliant. Cheers. Thank you very much, everyone.
okay. Bye, everybody.
Bye.
Bye-bye.
Thanks.